March 10, 1944, Wichita, Kansas. General Henry Hap Arnold, commanding general of the United States Army Air Forces, stood on the frozen tarmac of Boeing Plant 2, staring at 97 B-29 Superfortresses, the most advanced bomber ever conceived. Each aircraft represented over 1.5 million man-hours of labor, 40,000 separate parts, 600,000 rivets, and 9 miles of electrical wiring. They should have been ready for combat. They should have been preparing to strike Japan. Instead, only 16 could fly. The rest sat grounded, waiting for modifications that would take weeks in conventional repair depots. Arnold faced an impossible deadline. President Roosevelt had promised Generalissimo Chiang Kai-shek at the Cairo conference that American bombers would be attacking Japan from Chinese bases by spring. The promise carried strategic weight far beyond the bombers themselves. China, fighting Japan since 1937, was on the edge of collapse. Without American air power demonstrating commitment, Chiang might negotiate a separate peace, freeing hundreds of thousands of Japanese troops to defend the home islands against the coming Allied invasion. Arnold had staked everything on the B-29. The program had already cost $3 billion, exceeding even the Manhattan Project's budget by more than $1 billion. Now, standing among aircraft that couldn't fight, he made a decision that would violate every principle of aircraft production the aviation industry had developed over 4 decades. He would pull 600 skilled workers off the assembly lines. He would halt all other work. He would send aircraft directly from factories to modification centers for immediate rebuilding rather than completing them properly before delivery. He would, in the eyes of every aviation expert, sabotage his own production system. The mathematics appeared to defy logic. Removing workers from assembly lines should slow production. Delivering incomplete aircraft to modification depots should create chaos. Flying bombers directly from factories for extensive modifications rather than finishing them first should waste time, money, and resources. Yet within 40 days, this approach would reduce B-29 production time by more than 40% compared to conventional methods, transforming a program on the verge of cancellation into the weapon that would bring Japan to its knees. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The revolution that saved the B-29 program began with a fundamental misunderstanding about aircraft production that had persisted since the Wright brothers first flew at Kitty Hawk. For 40 years, aviation manufacturers had assumed that complex aircraft required complete assembly in sequence, with each component finished before the next began. This belief had shaped every production facility built, every training program developed, every workflow designed. Boeing itself had followed these principles, building thousands of aircraft. The approach had worked for simpler designs. It would prove catastrophically inadequate for the Superfortress. The B-29 represented a quantum leap in aviation technology. It was the first aircraft with a fully pressurized cabin, allowing crews to fly in comfort at altitudes where enemy fighters couldn't reach them. It featured the first central fire control system, with remote-controlled gun turrets directed by analog computers. It incorporated radar bombing systems, sophisticated communication equipment, and engines delivering power levels that would have been impossible just 5 years earlier. Each B-29 required 12 tons of aluminum sheeting, over 1,000 pounds of copper, approximately 9 miles of wiring, and 2 miles of tubing for hydraulic and pneumatic systems. The complexity created unprecedented challenges. When Boeing engineers examined the B-17 Flying Fortress production system in early 1941, they recognized immediately that traditional methods couldn't handle the Superfortress. The B-17 used approximately 15,000 separate parts. The B-29 required 40,000. The B-17's wiring could be installed by teams working sequentially through the fuselage. The B-29's 9 miles of wiring needed coordination among dozens of specialists installing systems simultaneously throughout the aircraft. Boeing production engineer H. Oliver West proposed a radical solution he called multi-lining. Instead of building aircraft sequentially from nose to tail on a single assembly line, West designed a system where 6 separate production lines fabricated major sections simultaneously. Forward fuselage sections moved down one line, wing assemblies progressed on another, tail sections, engine nacelles, landing gear assemblies, and interior equipment each had dedicated lines. Only at the final stage would cranes lift these massive sections, some weighing more than 150 tons, into position where they would be joined together. Traditional aircraft manufacturers considered West's proposal absurd. The Willow Run plant in Michigan, where Ford Motor Company built B-24 Liberators on the world's longest assembly line, stretched 3,700 feet. Engineers there had proven that moving aircraft through sequential stations maximized efficiency. West's approach required enormous factory floor space, excessive crane capacity, and complicated logistics coordinating 6 separate production streams. It violated every economy of scale principle industrial engineers had established. What the critics failed to understand was that West hadn't designed a system to build aircraft efficiently under normal circumstances. He had designed a system that could accommodate constant change, and change was about to become the defining characteristic of B-29 production. The first B-29 rolled off Boeing's Wichita assembly line in September 1943. Within weeks, testing revealed problems. Engine cooling systems overheated, starting fires that destroyed the second prototype, killing test pilot Edmund Allen, his 10-man crew, 20 workers at a nearby meatpacking plant, and a Seattle firefighter. The pressurization system leaked, gun turrets jammed, radar systems malfunctioned, plexiglass nose panels distorted, making it impossible for bombardiers to aim accurately or pilots to judge altitude during landing. Boeing engineers developed fixes, but implementation required modifications to aircraft already built. Under traditional production methods, each improvement would require stopping the assembly line, retraining workers, modifying tooling, and then resuming production with updated specifications. Completed aircraft sitting at airbases would remain unmodified until they could be returned to factories for rebuilding, a process taking months. By the end of 1943, Boeing, Bell Aircraft and Martin had delivered almost 100 B-29 seconds to the Army Air Forces. Only 15 were airworthy. The rest sat at various locations waiting for parts, waiting for modifications, or parked on the massive delivery apron at Wichita pending urgent fixes. Changes came so fast that B-29 seconds flew directly from assembly lines to modification centers for extensive rebuilds, incorporating the latest improvements. The system was drowning in its own complexity. General Arnold had visited Wichita on January 11, 1944. Walking through the plant, he had selected the 175th fuselage section on the line and signed it, telling workers, "This is the plane I want. I want it before the 1st of March." 2 months later, returning to Kansas, he discovered that not a single B-29 was combat-ready. Most sat scattered across modification centers throughout Kansas, waiting for parts that were weeks away. Some had been grounded for more than 2 months. Arnold exploded. The fate of America's strategic bombing campaign against Japan hung on getting B-29 seconds operational. Chinese airfields, built by hand with crushed rock spread by thousands of workers carrying baskets, awaited bombers that couldn't fly. Roosevelt's promise to Chiang was about to be broken. The entire $3 billion investment appeared wasted. Arnold placed Brigadier General Bennett Myers in charge with a simple directive: fix this immediately, using any method necessary. Myers examined the situation with fresh eyes, unclouded by aviation industry assumptions. The problem wasn't that the B-29 was too complex to build. The problem was that Boeing, Bell and Martin were trying to build a finished aircraft on assembly lines while simultaneously developing improvements based on testing. Every modification discovered during flight testing created a cascade of retrofit requirements for aircraft already built. Traditional production methods assumed stable designs. The B-29 was evolving daily. Myers realized that West's multi-line production system, designed to handle complexity, also created an unexpected capability for handling change. Because major sections were built separately and joined only at final assembly, Modifications could be incorporated into different sections at different times, without stopping entire production lines. A change to the nose section could be implemented on that line, while wings continued production using existing designs. More importantly, the separation between fabrication and assembly suggested a radical new approach to the modification problem. What if aircraft intentionally left the assembly lines incomplete? What if bombers flew directly to modification centers, where they would be finished using the latest specifications, rather than requiring retrofits of systems already installed? Under traditional thinking, this made no sense. It meant delivering unfinished products. It meant duplicating work, installing systems at modification centers that should have been installed at factories. It meant throwing away every efficiency principle that made mass production possible. But Myers saw something traditional manufacturers missed. Installing a new component in an empty aircraft space took minutes. Removing an old component, ripping out its wiring and hydraulic connections, then installing a new system took hours or days. By delivering deliberately incomplete aircraft to modification centers, Boeing could avoid the most time-consuming work, removing systems that would immediately become obsolete. The approach required fundamentally reimagining what a production line should produce. For 40 years, aircraft factories had tried to build finished airplanes. Myers proposed that Boeing Wichita should build unfinished airframes that would be completed at modification centers using the latest specifications. The factory wouldn't sabotage production. It would create a new kind of product, a platform that could be finished quickly rather than a complete aircraft that would need extensive modification. Arnold approved the plan. On March 9, 1944, 600 skilled workers were pulled from Wichita assembly lines. These workers, who understood B-29 systems better than anyone at modification centers, deployed across Kansas to the facilities where grounded aircraft waited. Subcontractors received orders to halt all work except B-29 components. Parts began flowing to Kansas by aircraft, train, and truck. The B-29 program was about to become the highest priority in the United States military, superseding even the Manhattan Project. Over 1,200 technicians, specialists, and mechanics converged on Kansas airfields during March and April 1944. They faced brutal conditions. Winter blizzards howled across the plains. Temperatures dropped below zero. Most modification centers lacked hangars large enough to house the giant bombers, requiring work outdoors in freezing weather. Ice formed on tools. Metal components contracted in the cold, making precise assembly nearly impossible. Workers wore multiple layers of clothing, warming frozen hands over fires between tasks. The modifications themselves were extensive. Wing structures required reinforcement. Engineers had discovered that stresses during high-altitude flight were causing microfractures in wing spars. Each aircraft needed wing skins removed, reinforcement plates installed, and skins riveted back into place. The work required drilling out thousands of rivets, modifying internal structures, then installing new rivets with precise tension tolerances. In sub-freezing temperatures, achieving proper rivet tension was extraordinarily difficult. Engine cowl flaps, which controlled airflow around the Wright R-3350 engines, needed redesign. The engines ran hot, causing fires that had already destroyed the second prototype and damaged dozens of other aircraft. New cowl flaps had to be fabricated and installed on every B-29, a process requiring removal of engine nacelle panels, modification of support structures, installation of new flaps with revised operating mechanisms, and testing to ensure proper function. Every plexiglass nose panel had to be replaced. The original panels, manufactured under rushed schedules, contained distortions that bent light like funhouse mirrors. Bombardiers couldn't aim accurately. Pilots misjudged altitude during landing approaches, causing several accidents. Each new panel had to be precisely fitted, sealed against pressure leaks, and tested. The work required extraordinary precision. A single improperly installed panel could cause catastrophic pressurization failure at altitude. Electrical systems needed rewiring. Fire control computers required recalibration. Radar bombing systems, Cutting-edge technology still in development needed replacement with updated versions. Gun turrets needed adjustment to improved specifications. Tires needed upgrading to handle the aircraft's enormous weight during takeoff and landing. Propellers required replacement with stronger designs. The list of modifications seemed endless. Yet the approach that seemed like sabotage began producing extraordinary results. Because Boeing's Wichita line now delivered aircraft with certain systems deliberately left unfinished, modification centers received bombers that needed installation rather than replacement. Workers who previously spent days removing obsolete components now spent hours installing new ones directly. The time savings proved dramatic. Aircraft that would have required 6 weeks of modification using conventional retrofit approaches were completing modifications in 10 days. Even more significantly, Boeing's assembly lines accelerated, removing the 600 specialized workers who had been installing complex systems that would need immediate modification freed assembly line capacity. Those workers, now at modification centers, installed the latest versions of systems directly. The assembly lines, freed from installing components that would become obsolete, focused on building high-quality airframes, engines, and basic structures. Production time per aircraft, measured from first component to delivery to modification centers, dropped dramatically. The first combat-ready B-29 emerged from the modification program in late March 1944. It departed immediately for India, beginning the 11,500-mile journey to bases being prepared for the strategic bombing campaign. More aircraft followed. By April 15th, 150 B-29 seconds were combat-ready and either deployed or en route to the China-Burma-India theater. Arnold had won what would become known as the Battle of Kansas. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The success in Kansas transformed not just B-29 production, but American thinking about mass production of complex weapons. Boeing's Wichita plant, now optimized for delivering incomplete airframes to modification centers, achieved production rates that shocked aviation experts. By war's end, Wichita produced 4.2 Superfortresses per working day, averaging 100 per month. More remarkably, labor hours required to produce each aircraft dropped from 157,000 hours for the first 100 bombers to less than 20,000 hours by 1945, a reduction of more than 87%. The multi-line production system proved its power. Where Ford's Willow Run plant with its single massive assembly line struggled to accommodate design changes, Boeing's 6 separate production streams adapted continuously. When engineers developed improved wing designs, the wing line implemented changes while other lines continued producing using existing specifications. When radar systems required updating, the electronics line incorporated new equipment, while fuselage production remained unchanged. The system that appeared inefficient under static design assumptions proved extraordinarily efficient under conditions of constant evolution. Other manufacturers adopted the approach. Bell Aircraft's Marietta, Georgia plant implemented multi-line production for its B-29 assembly. Martin's Omaha, Nebraska facility followed suit. By the war's end, 4 major plants, Boeing Wichita, Boeing Renton, Washington, Bell Marietta, and Martin Omaha, had produced 3,970 B-29 seconds, using production systems that intentionally delivered aircraft for completion at modification centers, rather than attempting to build finished products that would immediately need extensive modification. The strategic impact exceeded even Arnold's ambitious hopes. B-29 seconds, based in the Mariana Islands, conducted the most devastating bombing campaign in history. From November 1944 through August 1945, Superfortresses flying from Tinian, Saipan, and Guam systematically destroyed Japan's industrial capacity. Low-level firebombing raids devastated Japanese cities. High-altitude precision strikes demolished factories, refineries, and transportation infrastructure. Aerial mining campaigns cut supply lines, starving Japan of resources. 2 B-29 seconds, Enola Gay and Boxcar, delivered atomic bombs to Hiroshima and Nagasaki, ending the war. The aircraft that almost died in Kansas modification centers proved decisive in forcing Japan's surrender. Without the B-29 seconds, American forces would have needed to invade Japan's home islands, an operation projected to cost hundreds of thousands of American casualties and potentially millions of Japanese deaths. The strategic bombing campaign, enabled by aircraft that were sabotaged during production, provided an alternative to invasion that saved countless lives. The lessons Boeing learned in Kansas echoed far beyond World War II. The principle that complex products under rapid development should be built as adaptable platforms rather than finished systems influenced decades of aerospace manufacturing. When Boeing developed the B-47 Stratojet in the late 1940s, engineers designed production systems assuming continuous modification throughout the manufacturing process. The aircraft industry abandoned the assumption that designs must be frozen before production begins. The multi-line production approach pioneered by Oliver West became standard practice across aerospace manufacturing. When Boeing built the 707 jetliner in the 1950s, the company used parallel production lines for fuselage sections, wings, tail assemblies, and interior installations. The same principles applied to the 727, 737, 747, 767, 777, and 787 programs. Every modern Boeing commercial aircraft traces its production methodology to concepts developed under wartime pressure in Wichita. The deliberate delivery of incomplete aircraft for final assembly at separate facilities became institutionalized across the aerospace industry. Modern aircraft manufacturers routinely deliver major assemblies, fuselage sections, wing boxes, and tail units to final assembly centers where they are joined and completed using the latest systems. Airbus builds wings in Wales, fuselage sections in Germany, tail assemblies in Spain, and delivers everything to Toulouse or Hamburg for final assembly. Boeing builds fuselage sections in Kansas and South Carolina, wings in Japan, and tail assemblies in multiple locations before final assembly in Washington or South Carolina. The approach extends beyond commercial aviation. Military aircraft programs from the F-15 through the F-35 use distributed production with final assembly and systems integration at centralized facilities. The model that emerged from the Battle of Kansas, incomplete platforms completed at specialized centers, has become fundamental to how the world builds complex aircraft. Beyond aviation, the B-29 experience influenced thinking about managing technological complexity under time pressure. The program demonstrated that when technology evolves faster than production cycles, attempting to build finished products creates bottlenecks. Better to build adaptable foundations that can be finished using the latest developments. This insight shaped approaches to rapid military procurement during the Cold War and influenced commercial product development across industries facing accelerating technological change. The workers who fought the Battle of Kansas carried their experience into peacetime careers that transformed American industry. Many became supervisors, managers, and engineers at Boeing's growing commercial aircraft division. Others joined the emerging aerospace industry, bringing production expertise to companies developing missiles, rockets, and spacecraft. Some founded manufacturing businesses applying lessons learned, modifying B-29 seconds to peacetime products. The skills developed under emergency conditions proved valuable across industries, requiring rapid integration of complex systems. The women who joined aircraft production during the war faced particular challenges. Social expectations of the 1940s assumed women would return to domestic roles after victory. Yet many women who learned advanced manufacturing skills during the war refused to abandon capabilities they had proven. They fought for positions in post-war manufacturing, engineering, and technical fields. While discrimination remained pervasive, the war demonstrated that skilled technical work wasn't inherently gendered. The B-29 program employed thousands of women in roles previously reserved for men, from riveting and welding to electrical systems installation and quality inspection. Their wartime contributions opened doors that remained partially open afterward, creating pathways for future generations. The Battle of Kansas also revealed something profound about organizational capability under crisis. Boeing, Bell, and Martin had been building aircraft for decades before World War II. They employed experienced engineers, skilled craftsmen, and knowledgeable managers. Yet, when the B-29 program faced catastrophe in early 1944, salvation came not from refining existing methods, but from abandoning them. The companies that had built thousands of aircraft using conventional approaches succeeded with the Superfortress only by rejecting conventional wisdom. General Myers and his team succeeded because they asked a question traditional manufacturers considered absurd: what if we stopped trying to build finished aircraft? Every aviation expert knew that factories should deliver complete flight-ready airplanes. Every production textbook emphasized efficiency through minimizing handling, reducing transportation, and avoiding duplicate work. Myers violated all these principles by deliberately delivering incomplete aircraft to modification centers for final assembly. The approach appeared wasteful, inefficient, and counterproductive. It reduced production time by more than 40%. The paradox revealed that conventional efficiency metrics often measure the wrong things. Traditional aircraft production measured efficiency by time spent on each task, material waste, and rework required. These metrics made sense for stable designs, where each aircraft matched the previous one. They became misleading when applied to rapidly evolving designs, where every aircraft needed extensive modification after completion. By those traditional metrics, Boeing's approach of delivering incomplete aircraft looked disastrous. It involved transportation costs, duplicate handling, and deliberately incomplete work. Yet it dramatically reduced the time from design freeze to combat-ready aircraft, which was the metric that actually mattered. The experience demonstrated that true efficiency isn't about optimizing existing processes. It's about designing systems appropriate to actual conditions. When conditions involve stability and repetition, traditional efficiency metrics work well. When conditions involve rapid change and constant evolution, different approaches prove superior. The Battle of Kansas taught American manufacturers to question whether their efficiency metrics measured what truly mattered. This lesson proved crucial during the Cold War. American defense contractors faced continuous pressure to develop weapons, incorporating the latest technology while maintaining production schedules. The Soviet Union could match American technology, but struggled to match American production speed. Part of America's advantage came from production systems designed for continuous change rather than static repetition. Those systems traced directly to lessons learned in Kansas during spring 1944. The economic impact of the B-29 program rippled through communities across America. Wichita, Kansas grew from a regional center of approximately 115,000 people in 1940 to a major industrial city. The Boeing plant employed over 15,000 workers at peak production, supporting industries, housing construction, retail businesses, and services expanded to accommodate the boom. After the war, Boeing's continued presence anchored Wichita's economy for decades. The city became known as the air capital of the world, hosting not just Boeing but also Cessna, Beechcraft, and numerous aerospace suppliers. Marietta, Georgia, experienced similar transformation. Bell Aircraft's B-29 plant employed over 28,000 workers at peak production. The facility later became Lockheed Martin's Georgia assembly plant, producing C-5 transport aircraft, F-22 fighters, and C-130 variants. The economic foundation laid by B-29 production sustained the region for generations. Omaha, Nebraska's Martin plant employed thousands building B-29 seconds. After the war, the facility became part of what is now Offutt Air Force Base, headquarters of United States Strategic Command. The military presence and aerospace industry concentration around Omaha traced directly to the B-29 program. Renton, Washington, Boeing's other B-29 assembly plant, continued aircraft production through the present day. The facility built B-50 Superfortresses, C-97 cargo aircraft, and 707 jetliners after the war. Modern 737 production occurs at Renton, making it one of the longest continuously operating aircraft factories in the world. The town of 15,000 people in 1940 grew into a city exceeding 100,000, driven largely by aerospace employment. These economic impacts extended beyond direct employment. Each aerospace worker supported multiple jobs in construction, retail, education, healthcare, and services. The skilled workforce created by B-29 production attracted other industries seeking trained labor. Universities expanded engineering programs to supply the aerospace industry with graduates. High schools developed technical education programs, preparing students for manufacturing careers. The educational infrastructure built to support wartime production became a permanent asset benefiting communities for decades. The B-29 program also drove technological innovation beyond aviation. The analog computers developed for the aircraft's fire control system influenced early digital computer development. Engineers who worked on B-29 radar systems later contributed to civilian radar applications in weather forecasting and air traffic control. Pressurization technology developed for the Superfortress informed commercial airliner design. Remote control systems pioneered in B-29 gun turrets influenced automation development across industries. Materials science advanced through B-29 requirements. The aircraft demanded aluminum alloys stronger and lighter than previously available. Metallurgists developed new formulations that became standard across aerospace and later in automotive, construction, and consumer products. Quality control methods developed to ensure B-29 component reliability influenced manufacturing processes industry-wide. Statistical quality control, pioneered during wartime aircraft production, became fundamental to post-war American manufacturing excellence. The supply chain complexity required for B-29 production created new approaches to logistics management. Boeing, Bell, and Martin coordinated thousands of subcontractors, producing everything from massive wing sections to tiny electrical components. Managing this network required sophisticated tracking systems, communication protocols, and coordination mechanisms that influenced supply chain management theory for decades. Modern, just-in-time, manufacturing and lean production owe debts to practices developed managing B-29 component flows. Perhaps most significantly, the B-29 program proved that American industrial capacity, often described as fixed or limited by resource constraints, was actually highly elastic when necessity demanded. Before World War II, military planners assumed aircraft production capacity couldn't expand rapidly. Skilled labor took years to train. Factory construction required enormous capital investment. Tooling for complex aircraft took months to develop. These constraints suggested production capacity was relatively fixed in the short term. The B-29 program shattered these assumptions. Boeing built its Wichita plant in 18 months, beginning production before construction finished. Workers with no aircraft experience learned specialized skills in weeks rather than years through focused training on specific tasks. Tooling that would conventionally require months was designed and built in weeks under crash programs. When the program faced crisis in early 1944, production capacity expanded dramatically within 40 days by reorganizing systems rather than building new facilities or training new workers. The demonstration that industrial capacity could expand rapidly through reorganization and prioritization rather than just new investment proved strategically crucial during the Cold War. Soviet military planners, analyzing American industrial potential, consistently underestimated how quickly American industry could respond to threats. They saw the factories, counted the workers, measured the resources, and concluded American production capacity was impressive but quantifiable. They missed the organizational flexibility that allowed capacity to expand far beyond apparent limits when necessary. This miscalculation influenced Soviet strategic thinking throughout the Cold War. Soviet planners designed military forces to overwhelm American production capacity in a prolonged conflict. They failed to account for the possibility that American industry could reorganize itself to achieve output levels far exceeding peacetime capacity. The B-29 experience, though never cited explicitly in Soviet military analysis, represented exactly the kind of adaptive capability Soviet planners consistently underestimated. The aircraft themselves mostly disappeared after the war. Of 3,970 B-29 seconds built, only 22 survive today. Most were scrapped within a decade of war's end, their aluminum recycled into civilian products. A few served in the Korean War before retirement. Some were converted to tanker aircraft, weather reconnaissance platforms, or engine test beds before eventually scrapping. The B-50 Superfortress, essentially a re-engined B-29, extended the design's service life into the 1960s, but these aircraft too eventually retired. 2 B-29 seconds still fly. Fifi, owned by the Commemorative Air Force, and Doc, owned by Doc's friends, both based in Wichita. These aircraft, maintained by dedicated volunteers and donors, serve as flying museums demonstrating the technology that helped end World War II. Watching them fly provides tangible connection to the era when these massive bombers filled Pacific skies, their polished aluminum fuselages gleaming in sunlight as they approached targets thousands of miles from base. The handful of B-29 seconds preserved in museums worldwide represent merely a tiny fraction of the nearly 4,000 built. Each surviving aircraft stands as testament not just to the bomber's strategic impact, but to the industrial achievement that produced them. These aircraft, complex beyond anything previously attempted, reached production at a time when most experts considered mass production impossible. They achieved combat readiness only because engineers, managers, and workers abandoned conventional wisdom about how aircraft should be built. General Curtis LeMay, who commanded B-29 operations against Japan, reflected in his post-war memoir that the Superfortress campaign succeeded because of industrial capacity rather than tactical brilliance. Japanese defenses could have stopped small bomber formations. They couldn't stop waves of hundreds of B-29 seconds appearing night after night, month after month. American industry replaced losses faster than Japanese defenses could inflict them. The mathematics of attrition favored the side that could produce aircraft quickly over the side that could shoot them down occasionally. This strategic reality traced directly to decisions made in Kansas during spring 1944. Had Arnold accepted conventional wisdom and continued traditional production methods, B-29 seconds would have reached combat months later in far smaller numbers. Japan would have had additional time to strengthen defenses, fortify positions, and prepare for invasion. The war would have lasted longer, costing more lives on both sides. The atomic bombs, eventually delivered by B-29 seconds, would have been dropped by aircraft that existed only because Boeing deliberately sabotaged traditional production methods in favor of approaches that worked, despite violating every efficiency principle conventional manufacturers held sacred. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The story of why American factories sabotaged B-29 assembly and produced aircraft 40% faster is ultimately a story about questioning assumptions. For 40 years, aircraft manufacturers had assumed that building finished products on assembly lines represented the most efficient approach. For 40 years, nobody had built aircraft complex enough to test that assumption under conditions of rapid technological change. When the B-29 program reached crisis, salvation came from engineers willing to ask whether the assumption still held. The answer proved to be no. Under conditions of rapid change, building incomplete platforms for final assembly at specialized centers worked better than building complete products requiring extensive modification. The approach looked like sabotage because it violated every conventional efficiency metric. It succeeded because those metrics measured the wrong things. True efficiency meant getting combat-ready aircraft to cruise as quickly as possible, not minimizing handling or avoiding duplicate work. Boeing's workers in Wichita, many of whom had never touched an airplane before the war, achieved what veteran aircraft manufacturers considered impossible because they weren't constrained by knowledge of what supposedly couldn't be done. The farmers, housewives, shop clerks, and laborers who built B-29 seconds didn't know that aircraft production required years of apprenticeship, that complex systems needed sequential assembly, that designs must be frozen before production begins. They simply learned the specific tasks assigned to them and performed those tasks as efficiently as possible within production systems, designed for continuous change rather than static repetition. That ignorance of traditional constraints became a tremendous advantage. When crisis demanded radical solutions, Boeing's workforce adapted quickly because they had no investment in conventional methods. When engineers proposed delivering incomplete aircraft for final assembly elsewhere, workers implemented the approach without resistance because they had no preconceptions about how aircraft production should work. The revolutionary production system that saved the B-29 program succeeded partly because the people building aircraft under that system didn't know it was supposed to be impossible. The legacy endures wherever industries face the challenge of mass-producing complex products under conditions of rapid technological change. Modern manufacturing confronts this challenge constantly. Consumer electronics, medical devices, telecommunications, equipment, and countless other products must reach market quickly, despite incorporating technologies still under development. The approaches used vary by industry, but the principle remains constant. When technology evolves faster than production cycles, building adaptable platforms proves superior to building finished products. This principle, demonstrated under fire in Kansas during spring 1944, represents one of World War II's most significant industrial innovations. The Liberty ships and Victory ships that kept supply lines open, the atomic bomb that demonstrated new weapons' destructive potential, the radar systems that won the Battle of Britain, all represented crucial technological achievements. But the B-29 production system represented something different, a fundamental reimagining of how to manufacture complex products under time pressure with continuously evolving technology. That reimagining, born of desperate necessity when conventional approaches failed, transformed not just aircraft production, but American industrial capability broadly. It demonstrated that production systems themselves could be revolutionary, that questioning assumptions about efficiency could yield breakthrough results, and that sometimes the path to success requires deliberately violating principles that conventional wisdom considers inviolable. The B-29 Superfortresses are mostly gone now, scrapped decades ago or resting on museum display floors. But the revolution they represented endures in every modern aircraft factory, in every manufacturing facility that uses distributed production with final assembly at centralized locations, in every industry that builds platforms for completion rather than finished products requiring modification, and in every manager who questions whether impossible truly means impossible or simply means nobody has figured out how yet. That is the enduring legacy carved not in aluminum, but in transformed understanding of what dedicated people can accomplish when freed from the constraints of tradition and challenged to attempt what experts claim cannot be done. From September 1943, when the first B-29 rolled off Wichita assembly lines, to April 1944, when the Battle of Kansas produced combat-ready aircraft, to August 1945, when Superfortresses delivered atomic bombs that ended the war, Boeing proved that industrial revolutions happen not through incremental improvements, but through fundamental reimagining of what is possible. The 3,970 B-29 seconds built between 1943 and 1946 carried more than bombs across oceans. They carried proof that human ingenuity, when unshackled from tradition and empowered by necessity, can accomplish what conventional wisdom declares impossible, and that sometimes the path to extraordinary achievement requires deliberately sabotaging conventional approaches in favor of revolutionary alternatives that work precisely because they violate every rule traditional experts consider sacred.